Hello, everyone. And I wanted to give an example of this non-homogeneous linear recurrence relation and use two methods to solve it. So the equation, the recurrence relation goes like a sub n equals 2 times a sub n minus 1 plus 3 times a sub n minus 2 plus 2 times n times 3 to the n. With two initial values, a0 equals 0, a1 equals 1. We have a degree, which is 2, so we only need two initial values. Let's have a look at two theorems I wanted to use. So let's share different share. Okay, so this is the theorem when I use the first for the first method. You look at the left side, which is the homogeneous part, with degree of the recurrence relation to be k, and then the right side has a form of a polynomial b sub n, b of n, p of n times b to the n. And the example we have earlier, which is like this, was Pn to be 2 times n and 3 to the n, b is 3. So in our example, I'm going to just write down this example there. We have a sub n equals 2a sub n minus 1 plus 3a sub n minus 2 plus 2 times n times 3 to the n. Okay, so the homogeneous part is a sub n minus 2 a sub n minus 1 minus 3 a sub n minus 2. And b equals 3, and p of n is a polynomial. Here is 2 times n. If you don't see 2 times n in front of 3 to the n, you're going to treat p of n to be 1. It's still a polynomial. And if you don't see 3 to the n, you're going to treat it as a 1 to the n. So b equals 1. Okay. So for this problem, we're going to simply write down the characteristic equation once for all. Okay. This is the characteristic equation. So we use T or R, doesn't really matter. Okay, we can use R squared because you have a degree of the recurrence relation to be 2. So R squared plus, actually minus 2 times R minus 3. This is the homogeneous part. And the non-homogeneous part is R minus B, B is 3. And m is the degree of the polynomial. Here, the degree of the polynomial is 1. So 1 plus 1, you get a 2. So you have r minus 3 squared equals 0. And then you know that you factor out two terms. You have r plus 1 times r minus 3. Okay, and then you combine with r minus 3 squared, you get 3 to the third. Okay, r minus 3 to the third. How to factor out a quadratic expression? There's several ways. I'm not going to talk more about it. You can use ad hoc, just try and error, or you can use the quadratic formula, or you can use completing the square. So there are different ways of doing that. I'm not going to talk about that for here. So anyway, we have two roots, r1 equals -1, and r2, 3, 4, okay? There's multiplicity 3 for root 3, okay? And then we can follow the theorem, which is once you have the the roots are like that, you can write down the general solution, which is, so I'm going to need more space. I'm going to erase that one and write down the general solution. A sub n equals C1 times -1 to the n plus C2 times and then our times 3 to the n, that's fine, but we're going to combine 3 to the n. So C2 plus 3 times n plus C4 times n squared times 3 to the n. Okay, so this is one of the theorems earlier. So let's see if we can find that one. It's somewhere here. Right, that is with without multiplicity. So with multiplicity, we have the theorem. Okay, and you can see we have two roots, R1, which is -1, R2 is 3. And then the multiplicity of -1 is just 1. So you have only a constant here, which is C1 here. And for root 3, the multiplicity is 3. So you have n squared, you have a quadratic expression here. You can say C2 plus C3n plus C4n squared, because m2 minus 1 is actually 3 here. 2 here, sorry. M2 is 3. Multiplicity is 3. Okay. So let's erase that one and go back to the slide. I don't think we need more slides for the moment. So remember this thing, I want to copy to the whiteboard. Okay. And then we use initial values to solve. All right, so let me stop share this one and share whiteboard. Okay. All right, so let's do, I don't like, I like blue color. All right, so we have this general solution A sub n equals C1 times -1 to the n. See, the pen seems to be odd. C2 plus C3. Let me see, is that better? Times, oh, no way. Times n plus C4 times n squared times 3 to the n. Okay. This equation has, this expression has 4 unknowns, C1, C2, C3, C3, C4. And we only have 2 initial values. We need 4 values, A0, A1, A2, A3 to solve C1, C2, C3, C4. That's fine. We can use the recurrence relation and 2 initial values to generate more values, more terms. For example, A2, you can generate it from 2 initial values and the recurrence relation. So 2 times A1 plus 3 times A0 plus 2 times n, which is 2 times 3 squared. So you have a 2 plus 3 times 0 is 0, plus 4 times 9, which is 36. I get 38. And then you keep doing that. A3 equals 2 times A2 plus 3 times A1 plus 2 times n equals 3, and 3 to the third n equals 3, okay? And that equals 2 times A2, which is 76. 3 times A1, A1 is 1, so that's 3, plus 6 times 3 to the third, which is 27. That is 79 plus 6 times 27, which is 162. And you add them up, you get 241. All right, so the algebra is a little bit involving, but we know how to do that, okay? So now we plug in, we find 4 equations, all right? So A0, which is 0 to the end. So you plug in 0 for n, you get -1 to 0 is 1. So C1 plus, you have n0, so that disappears. These two terms disappeared. And then 3 to the 0 is 1, so you get 1 times C2. That equals 0. And then you have A1. So you plug in 1, you get negative C1 plus C2 plus n equals 1. You have C3 plus C4 times 3. Okay, 3 to the 1 is 3. That equals 1. All right. And then you have A2 when n equals 2, -1 squared, you get 1, so you have C1 plus C2 plus n equals 2, you get 2C3 plus n squared is 4C4 times 3 squared, which is 9, equals 38. If you are tedious about this algebra, you can fast forward, I guess, but I needed to solve that. 3 equals n equals 3, so -1, so negative C1 plus C2 plus n equals 3, and then 9 C4 times n to the third, which is 27, we get 241. So I have 4 equations, and we want to solve these 4 equations, okay? For a second, I think I can move down. Let me get to move down. I think there's a way of moving down. All right. Well, actually, I need a little bit more. Okay, so let's organize these equations. And you have a negative C1 plus 3C2 plus 3C3 plus 3C4 equals 1. And then you have a C1 plus 9C2 plus 18C3 plus 36C4 equals 39. Sorry. It's weird. I wrote 36 and I said 38. I said 39, but actually the number should be 38. And then I have negative C1 plus 27C2 plus 3 times 27 is 81. C3 plus 9 times 27, 3 times 81, 243 times C4 equals 241. Okay, well, it's a bit tedious. From the first one, we see C1 equals negative C2. Okay, so I'm gonna replace all the C1s in the next three equations by negative C2. So it's negative C1 equals C2, so I have a 4C2 plus 3C3 plus 3C4 equals 1. It's simple linear algebra. It's a little bit tedious, but it's not that difficult. C1 equals negative C2, so you have 8C2 plus 18C3 plus 36C4 equals 38. And then negative C1, C2, so I have a 28C2 plus 81C3 plus 243 C4 equals 241. All right. Now, I'm going to use the first one, okay? Multiply by 2, you get 8C2. Multiply by 7, you get 28C2. So let's do that. We're going to get rid of C2 using method of elimination. So I have 8C2 multiplied by 2, okay? 6C3 plus 6C4 C4 equals 2. And you subtract this one from the original second equation. You would get, let me write somewhere here. So I get 12C3 plus 30C4 equals 36. Okay. And I'm going to multiply this equation by 7. I get 28C2 21C3 plus 21C4 equals 7. And you subtract these two equations, get rid of C2. I have 60C3 plus 222, okay? 222C4 equals 234. All right, you can simplify something here, but I'm kind of not in the mood, so I'm gonna just multiply this equation by 5. I get 60C3 plus 5 times 5, so 150 C4 180, and then subtract and get rid of C3. I have 72 C4 equals 54. All right, so you would get C4 to be I think for here for 18th, 3 out of 4. All right, and then I wanted to simplify this equation. Okay, to try to solve for C3. Okay, so let me erase that thing. Okay, all right, so I have a 6, 2C3 plus 5C4 equals 6. And C3, so 2C3 equals 6 minus 5 times C4, so 15 over 4. That's 24, so 9 over 4. C3 equals 9 over 8. All right. Okay, now we need to look at C2. So we're going to use this equation. So I'm going to be everywhere. So C4, C2 equals 1 minus 3C3 minus 3C4. That equals 1 minus 3 times C3. Well, let's do a slightly different way. 3 times C3 plus C4. 9 over 8 plus 3 over 4. 3 over 4 is 6 over 8. So you have 15 over 8. 1 minus 3 times 15, 45 over 8, negative 37 over 8. And then, we need to divide by 4. So I get C2 equals negative 37 over 32. Okay. 4 times 8, 32. And then we have C1 equals negative that, 37 over 32. All right, so finally we have A sub n equals 37 over 32 times negative 1 to the n, okay? Remember, let's move up, see this expression, C1 times negative 1 to n and so forth, okay? So let's move down, plus C2, which is negative 37 over 32, plus what? Plus C3, where's C3? So 9 over 8 times n plus 3 over 4 times n squared times, then parentheses times 3 to n. So this is our solution. So I don't have the mood to really check, okay? So I'm gonna just accept it. All right, so this is one way using the one of the theorems I covered in the class, but it's actually not in our textbook. Just you use the characteristic equation for the whole non-homogeneous recurrence relation. Okay. All right. So let's use the second method. Let's see. So the numbers are a bit tedious. Okay. Okay. So the theorem from the textbook is this one. So first of all, we are looking for a particular solution. Okay, this is the particular solution. Particular solution. The homogeneous part, it's from this thing, okay? And this is for that. All right. So I need another theorem. So move down, another theorem. Okay, so this is a theorem. So we have a non-homogeneous recurrence relation, okay? And Fn has this form, which is the polynomial times s to the n. It just have a different look. It has different look than what we had earlier, but essentially the same. It's a polynomial with degree t times s to the n. S is like b over the other theorem. Okay, and the result is when S is not the root of the characteristic equation of the associate linear homogeneous recurrence relation, then there is a particular solution of the form, which is a polynomial. Okay, it's a polynomial with the same degree but with different, well, general coefficients. May not be the same as b sub I, okay, times s to the n. When S is a root of this characteristic equation and its multiplicity is M, this M comes from the homogeneous part. Okay. And then a particular solution would be having the form of n to the m. M is the multiplicity, okay? And then multiply by this general polynomial with degree t, the same as the original degree of this piece of n, well, and the polynomial, and then times s to the n. Okay, what does that mean? So let's look at our recurrence relations. A sub n equals 2 times a sub n minus 1 plus 3 times a sub n minus 2 plus 2 times n times 3 to the n. Okay. So we know the characteristic equation for the homogeneous part is actually is r squared minus 2r minus 3. So it turns out, well, if we expand it, I mean, factor out two linear terms, is that this 3 is the same as this 3. So I'm going to use this part as is a root of this characteristic equation. The multiplicity is 1. The multiplicity for this piece is 1. So the particular solution, A sup parentheses P sub n, would be n to the m equals 1, okay? Multiplicity is 1 for this one. So you would have n times, this polynomial has degree 1, so this little t is 1. So when I just use alpha plus beta n, so it's a linear function, okay? Times 3 to n. So this is our particular solution. All right. We're gonna figure out alpha beta, okay, from the characteristic, from the recurrence relation. Okay. So let's move to the Y screen. Okay. Stop share. Let's share the whiteboard. The old one. So let's keep doing that. Okay. So we have this relation a sub n equals 2a sub n minus 1. I really don't like to write this n minus 1 plus 3a sub n minus 2 plus 2 times n times 3 to the n. All right, we have initial values, a0 equals 0, a1 equals 1, and we have a particular solution which has the form of, what is the form? It's called linear n times a linear function times 3 to the n, okay? All right, now, what are we gonna do? I wanted to move down. All right, so what we wanted to do is plug this particular solution to the original recurrence relation, and then equate the coefficients of certain the terms involving n, the terms involving n squared, and the constant term. Equate them and solve alpha and beta. Okay, so that's what we're gonna do. So plug into the original equation, original recurrence relation. So I left side will have n times alpha plus beta times n times 3 to the n equals 2 times a sub n minus 1. Okay, so you have n minus 1. You're going to replace that n by n minus 1 times alpha plus beta times n minus 1 times 3 to the n minus 1. And then I have 3 times a sub n minus 2. So you have n minus 2 times alpha plus beta times n minus 2. Then 3 to the n minus 2 plus 2 times n times 3 to the n. Okay. I'm going to divide both sides by 3 to the n minus 2. Okay. Divide by 3 to the n minus 2. So I would have 9 here, 3 here, and a 9 here. So I have a 9n times alpha plus beta times n equals 3 times 2, you have 6. Okay. I'm going to expand it. So I have a, oh, maybe another step. Yeah, it's a little bit tedious. Beta n minus beta. Okay. Plus 3 times n minus 2 times alpha plus beta n minus 2 beta. And then I have a 9, right? So 18n. Okay, 3 squared. Okay. So let me expand a little bit further. Okay. Let's do alpha n plus beta n squared minus beta n. Then I have minus alpha minus beta n plus beta plus 3 times alpha n plus beta n squared alpha n beta n squared minus 2 beta n. I wanted to move down further. Okay. Okay, so let me do again alpha n beta n squared minus 2 beta n, and then do minus 2 alpha minus 2 beta n plus 4 beta plus 18n. Okay. All right. So let's look at the coefficients. So here you have n here, and no constant term. So the constant term is actually 0. Well, yeah, it's 0. I'm going to look at the right side that doesn't have n. This one doesn't have n, so negative 6 alpha. This doesn't have n, so plus 6 beta. And then this one doesn't have n. This one doesn't have n. Minus 6 alpha plus 12 beta. Okay, you can simplify it. Negative 12 alpha. I'm going to move this to the right side, left side. You have a 12 alpha equals 18 beta. And I get alpha equals a 9 over 6, 3 over 2. So 3 over 2 beta. Okay. Let's work with the coefficient coefficient of n. So I have 9 alpha, okay, equals, remember this coefficient of n, you have n squared if you multiply it together. So 9 alpha. Okay, so all the terms with n, not n squared, okay? So I have a 6 alpha minus 6 beta minus 6 beta, okay? And then plus 3 alpha, and then you have a minus 6 beta, again 6 beta, and then plus 18, okay? There's some theory I wanted to maybe, it's good to mention that. If you have two polynomials, let's use a quadratic, okay? So you have a two quadratic, you have ax squared plus bx plus c. And you have another one, ax squared plus capital Bx plus capital C. If these two polynomials are exactly the same for all the values of x, then you can get little a equals capital A, little b equals capital B, little c equals capital C. That's how that's the reason I got these equations, okay? These equations. I was equating the coefficients of the terms, like in front of n, in front of n squared, just constant terms. Okay, all right. One more time, one more equation. I think we're able to solve alpha beta already, but okay, let me simplify this. You have alpha, get rid of alpha, 9 alpha is it's 0. And then you have a negative, -6, 6, 4 of them. Move to the left side, you have a 4 times 6, 24 beta equals 18. So you get beta equals 18 out of 24, 3/4. And then you would get alpha equals 9/8. Okay. Let's look at what we had earlier, and you see actually they're the same. Where is this? 9, you see here? 9, this one, okay? They're the same, so it's good news. All right, you can double check with the coefficients of n squared. I think we will get to, hold on a second. I'm gonna. All right, let's check the coefficients of n squared. So you have a 9 beta, okay? 9 beta n squared. Let's use a different color, okay? So you have n squared, n squared, that's n squared, that's it. Okay, so you have a 6 beta and then plus 3 beta. Okay, so this is identity, doesn't contribute to anything, but we don't need that. We already have had these two coefficients already. Okay, so we have this particular solution, a sub n with a particular, okay, equals, okay, remember, we have n somewhere, okay? I think 9, it should be 9/8 plus 3/4 n, and then there's another n, and times 3 to the n. So this is our particular solution, okay? Now we try to find the homogeneous one. Actually, we're gonna write down the whole solution a sub n equals the homogeneous one. Let's use a, capital A, times -1 to the n. Remember, The homogeneous one, you have r squared minus 2r minus 3, which equals r plus 1 times r minus 3. Okay. Plus b times 3 to the n. Okay. This is the homogeneous part. And then I have a non-homogeneous part. Okay. And then, all right. And we do have two initial values. For this method, we don't need to find A2 and A2 and A3. Okay, so we have A0 equals 0, A1 equals 1. Okay, so I have A0 equals, plug in 0, you have capital A and B. Okay, 3 to the 0 is 1, so A plus B. And here you have N, so it will be 0. So that equals 0. And A1, that equals negative A, because negative 1 to the first is negative 1. And then plus 3B plus N equals 1. So you have 9 A's plus 3/4 N equals 1, okay, times 3. That equals 1. So let's simplify it. Okay, so I have a negative A plus 3b. Actually, from the first equation, we know that a equals negative b. So negative a equals b. So this is actually 4b. Let's move the constants to the right side. Right, get 1 minus, so this is 6 over 8. So you have 15 over 8. 15 over 8 times 3. 15 times 3 is 45 over 8. So that's 48. 45 minus 8 is 37. So negative 37 over 8. And then you divide both sides by 4. You get b equals negative 37 over 32. And a equals negative b, which is 37 over 32. All right, then plug it back into this. I get a sub n equals a, so 37 over 32 times negative 1 to the n plus b, so negative 37 over 32. You actually can combine the last two terms. It is 9 over 8, right? It's 9 over 8. Times n, because you have n here, okay, n here, and then plus 3 over 4 n squared times 3 to the n. That's exactly the same as what we had earlier, okay? That's what it is. All right. So it's positive negative 1 to the n, negative 32 over, yeah, okay. So write up. It's the first method is theoretically it's pretty clear. You just write down the characteristic equation for the whole non-homogeneous recurrence relation, as long as the non-homogeneous part has the form of p of n, which is a polynomial, times b to the n. B is a constant. Okay, then you're able to write down the whole characteristic equation and you solve it and use the theorem which deals with distinct roots and the roots with multiplicity. You can write down the general solution very quickly. But sometimes the system of equation is big, and normally they will give you initial values that are only sufficient to are necessary to solve the equation, to solve the recurrence relation. But in order to solve the system of linear equation, which has like 4 here, so you needed to generate more terms, more values of a sub n to have enough information to solve for unknowns, the coefficients, okay, C1, C2, C3, C4. And sometimes it's a little bit more involving if you wanted to solve a large system of linear equation. Okay, but since theoretically, it's pretty clean. All right, now the second method, which is from our textbook, it solve a particular solution, and then you solve everything else. I would have to say that sometimes this method is better when uh, when it's easy to solve coefficients like that. Now you have 2 equations to solve alpha beta, and then later on you have another 2 equations to solve another 2 unknowns. So you're sort of having 2 smaller systems of linear equations. And sometimes it's advantageous. It's easier to do that. But for this one, it's not really beneficial because the first to solve alpha and beta, they actually need some work, get some algebra here to expand a bunch of things. But if we don't have this n, which means this 3 would be different from the root of the characteristic equation for the homogeneous part, then it would be simpler, okay? It would be simpler. But for this one, actually, I don't see the second method is much beneficial. But anyway, these are 2 methods. I hope you get a better idea about how to solve a system, solve a recurrence relation, the linear, non-homogeneous one. All right. All right. Thanks for watching, and I'll talk to you later. Bye-bye.